Hello everyone, welcome to your first calculus video. We're just going to be talking about limits, which is usually something they'll teach you first. The reason why we go over limits first is just because we'll use it a lot with topics like integration and derivatives to define it before just kind of using a bunch of rules to help you out with it. And limits aren't that crazy to understand. Limits is just this idea that what happens to f of x, which remember is just y. So what happens to f of x when x approaches some value? So when f approaches some value, what happens to the f of x value? And if this sounds familiar, it's because you've already technically been using it, you just didn't know you were using it. So let's just say you had any kind of point on a graph. Let's just say you had a line and the x value was maybe something like 2 and the y value was something like 4. Well, if I asked you on either side of this line, as x approaches 2, what's the y value going to be close to? It's going to be 4. So it's very similar to what you've already been doing. It's just instead of, you know, f of 2 being 4, it's just going to be when x approaches 2, what is f of x going to be as it approaches it. So it may not be that value, but what is it approaching? And that's kind of all a limit is. So they're going to give you three main ways to understand this. The first way is called numerical limits, and this is using a chart. Now it isn't always taught, but in case it is, this is the general idea. So let's just say we had an x value and we had an f of x value. And on this chart, let's say we had a value like 1.9, 1.99, 2 would be this one right here. We had maybe 2.01 and then 2.01. And then on the f of x side, we had something like 3.9, 3.99, maybe some sort of blank value right here. Then we had something like 4.001 and then 4.01. So it's pretty clear that as the x values get close to 2 right here, the f of x values are getting close to what it looks like 4. And that's all analytical limits are. They'll want you to try to use the chart to guess what the f of x value is as x approaches some number. And the reason they'll do this is because sometimes, as you've already seen, some graphs they have certain undefined values, which are called asymptotes. So in this case, we would have some sort of equation, and it would be something like f of x equals to x squared minus 4 over x minus 2. So if you notice, if we put 2 into this equation, it actually becomes undefined. We couldn't solve this. But using limits, we can find what the f of x value approaches using other values. And that's all limits are analytically. So we're using charts for analytical limits. After they give you analytical limits, they'll give you what's called graphical limits. And this is the same thing, it's just we're going to be using graphs to define what the limit is instead of simply any other, like a chart. Okay, so let's just say we had a very like a cubic graph, something you've already been exposed to. So in a standard cubic graph, let's just say we had a point 1, 1, and this is where the point is, let's just say. So if I told you as x approaches 1, just like our example at the beginning, you would tell me that the f of x value is 1 as well, let's just say, okay? And so that would be the graphical limits. But what they're going to start doing is they're going to give you some notation to work with. So let's just say, let's explain what that is. So what it is, the first part is this lim, it stands for limit. So we'll have this limit, we'll have this x here, you'll have an arrow, and you'll have whatever value x is approaching. So in this case 1, and then the f of x value, which is this one right here, is going to be right here. So the way you would read this is the limit as x approaches 1 is equal to 1. Okay, and that's, again, we were already doing this. We're just going to be showing it in a kind of like a written way. Okay, so let's just say we had that and we wanted to bridge on it. So the next thing they'll do is they'll introduce this little sign next to the x. So they'll have like a minus or a little plus. So what this says is its limit as x approaches 1 from the left. So from the left side would be from the left of this graph. So from the left of this graph, if we follow the graph from the left, well then we have it approaches a y value of 1. So it's still going to be 1. And let's just say from the right, which would be this little plus, well, it's still going to be 1 because if we follow the graph, it would still be 1. Okay? Now let's change it a little bit then, okay? So let's pretend like the point is instead what's this open circle. And if you've already done a little bit of algebra, you know that this is called a hole, where an asymptote usually is, or just sometimes it's a hole in the graph. So what would happen here? Would it still be the same? The answer is yes, it would still be the same because remember, it's not an f of x value, it's as it approaches it. So as we approach 1 from either side, we're still going to approach a value of 1. Okay? So they might try to trick you, but just because there is an open circle, it's the same thing. The limit is still defined here. Okay? Now let's move on to a different kind of graph. So let's just say we had something like let's say we had a graph that looks kind of weird, and it looks something like this. So we had open circle, and it's going to come out this way, and then it's going to be separated, and it's going to come out this way. Okay, so what would happen here? Well, if we wanted to know as it approaches, let's just say 0, well, we've come to a problem, because if we try to use our previous way, they're different. So if we have an x value here at 0, well, at 1, it seems to be 1 from this side and -1 from this side, the left side. So what will we write then if they're different? Well, if the limit is a different value on both sides, it's going to be what's known as DNE, which is called do not exist. And you would write that every time the limit is not the same on both sides. Okay, so we know it's DNE, but what would we do if instead we had something like, what if we put one of them instead? So if we said maybe 0 from the left side, well, 0 from the left, we can do that now. So from the left, at 0, it's approaching -1. So we would put -1 instead. And from the right, we would put 1. So that's what could happen if you do the limit and they're separated, kind of like a piecewise function. So let's say instead we had a different kind of graph. Okay, and we're going to practice this just because there's one other example they like giving to students. And you'll do these a lot more later. These are called infinite limits. So let's just say we had a very common graph, like f of x equals to 1 over x. So we have the graph of 1 over x. So 1 over x, we already know, looks something like this. And even if you didn't know what the limit would be, we do know that it's not going to be the same if we wanted to know at 0, because there's asymptotes here. But if instead we had something like 0 from, let's say, the left, well, from the left, we're going to be going, if we follow the graph, it's going down to the bottom infinitely. So this would be something like -infinity. And let's say instead we had 0 from the right. Well, we would go up and follow the graph, and obviously this would go to infinity, or positive infinity. So these are the three main types of graphical limits you can encounter. So the first type involves really just understanding that holes can not exactly stop a limit. The second one has to do with maybe the graph is separated with a discontinuity, and that would just mean that you would have differing values on both sides, and then you could have something similar, but instead of just one value, it's going to be more than one value, and that would be maybe infinite. And it's important to note that if we have infinity, technically this is a DNE. It's just a really specific DNE. It's saying that the value could be anything approaching infinity. Okay, so these are all the different ways you can understand limits graphically. The last thing that I'll introduce really quickly is what's called analytic limits, and these ones are a very large topic on their own right, but I'll go over the basic idea. So if we had something like the limit as x approaches, let's say 1, of x plus 2, how would you solve that? Now, we don't have a graph, we don't have a chart, so what would be the best way? Well, it turns out the best way to solve this would be to basically just plug this in. And what you have to do, though, and what you have to remember is that if you're not plugging something in right away, you have to keep writing it out. But since we can just plug it in, that's fine. So 1 plus 2 would be our plugging in, and then we get the answer as 3. So in this case, the limit value matches the f of value because there is no discontinuities, kind of like how we saw in that first graph. But let's just say instead, what if we had the limit as x approaches 0 of sine of x plus 1. So can it work with trig as well? It turns out it can. So if we plugged in 0, we'd have sine of 0 plus 1. We know that sine of 0 is 0, so 0 plus 1 is 1. Okay, so that works that way as well. Now I'm going to have a full video on exactly how it works with other limits. So what if we can't just plug it in directly? What happens then? It turns out there's some simplification we can do, but for now this is the general idea of how limits can work.